Yeah, that algebra review should be your first taste of proving for this class so far. All right. Let's just flip the light. I think we're done with the projector. Okay. So today we start chapter 3. We're starting geometry proper. We're starting to dip our toes into axiomatic systems. Now, an axiomatic system in general has 4 parts. We have what we call undefined terms. 2, we have theorems. 3, we have definitions. And 4, I don't know why I've listed this 4, should have listed a second. We have axioms, or in this class we'll call them postulates. Those are the 4 things that postulates and axioms one and the same thing. These are the 4 things every axiomatic system is composed of. Let's get a sense of what all of these are. So first off, if you go to a dictionary and you look up a word, what does it give you? It gives you a bunch of other words, right? Let's say I gave you a French dictionary. How many French words can you learn? I give you you look up one French word in the dictionary. It gives you a bunch of other French words. But you don't know any French words. So you go look up all those words. What do you get? More French words. You go look up all those words. What do you get? More French words. And one of 2 things is going to happen. Either 1, you're eventually going to get back to one of the words you were initially looking up. You're going to go in a loop. Or 2, you're in an infinite language and there's an infinite regress to more and more words. That's bad. So we can't define everything. Even in mathematics, we can't define everything. So we have to have what we call undefined terms. So if an undefined term is undefined, does that mean it's meaningless? It doesn't mean anything? The answer is no. The axioms or the postulates are what give it meaning. So axioms or postulates are stated assumptions about our undefined terms. We assume whatever these words mean, that they have these properties. And then, with our undefined terms, we can use our undefined terms to construct new definitions. All our definitions will be in terms of our undefined terms. So our undefined terms are our starting words, and we can use those to define new terms and new terms and new terms. So all our mathematical definitions ultimately come down to being defined in terms of our undefined terms. And then finally our theorems, that's the majority of math. That's just proving the implications of your axioms or postulates. So this is what every axiomatic system is composed of. So we start our axiomatic system today. First, I give you our undefined terms. So our undefined terms are our point, line, and plane. These are undefined terms, and between. We will have no definition for what these words mean. Go ahead.
We were asked to give an extra table.
An extra table?
Table? Yeah.
I have what you see before you.
Thank you.
Yep. All right. So these are undefined terms. We do not define these things. That doesn't mean that they're meaningless. We just can't define exactly what they are. They're given their meaning through their postulates or axioms. We're going to break our postulates up into postulate groups in this class. And then we will reference them via their group. So our first postulate group postulate group 1 is going to be our postulate group that relates lines, planes, and points to each other. So our very first postulate, which we will call postulate 1-1, is there are at least 3 non-collinear points on a plane. You know what it means for points to be collinear?
Yeah, they're on the same.
It means they're on the same line. So there's at least 3 points on the plane that can't be contained in one line. Point, point, point. You can't draw one line through those 3 points. That's our first postulate. Pretty straightforward, right? Second postulate. Sorry, postulate 1, 2. We're in postulate group 1. All right, postulate 1, 2 is a postulate that says every point has at least 2 lines. Oh, nope, sorry, that's number 3. Number 2 is for any 2 points, comma, there is exactly 1 line containing them. Or in other words, if I give you 2 points, there is one and only 1 line you can draw through those 2 points. And then 3 is that a line contains at least 2 points. So those are our 3 basic assumptions. Now I told you that points, lines, and planes here are undefined terms, and that all our other terms that we defined, we're going to use our undefined terms. I lied to you a little bit. We can use the terms of logic, always and forever, and we can use the terms of set theory, always and forever. It's understood that geometry is built on top of logic and set theory. So it's perfectly okay to talk about sets. It's perfectly okay to use your logical operations when you're talking about these things. And so it's understood when we're talking about these things that a plane is a set of points and that a line is a set of points. And a line being in a plane means a line is a subset of the plane. So lines and planes we think about as sets of points. Make sense? Okay. So now let's prove our first theorem. Theorem 3.1. So theorem 3.1, what does it say? It says 2 different lines do not intersect at more than 1 point. So 2 lines do not intersect at more than 1 point. All right. How are we going to prove this? Did I forget to start it? It's going.
So lines cannot bend.
Okay, perfect. You already said exactly what I was hoping you would. So we're saying, why is this an impossible picture? And he says, well, because lines have to be straight. Where did you get that information?
There's only 2 points.
No, I said 2 points define a line, so through any point, or through any 2 points, there's a line that goes through it.
Exactly 1 line. That's true, the line can be squirted.
So we have no notion yet of straightness, what it means for a line to be straight. Now, when we draw out our geometry, and we do some geometric proofing, you draw some figure. If I were to stick a fishbowl, imagine you always had a fishbowl in front of your eyes, and you always saw everything work that way, through that fishbowl. That doesn't change any of geometry. Every geometric proof you look at through that fishbowl lens is still just as valid as it ever was. We use pictures only to aid our thinking in geometry. We never actually rely on the picture. Now, it turns out that your intuition about lines have to be straight is going to be correct. But we have no notion of that built into our axioms right now. What it means for a line to be straight versus curved. So we're wondering, why is this an impossible picture? It's not because the lines are bending. That's not the problem.
It's not possible.
If this is a line and this is a line, then this is an impossible picture. So if this is line 1, And so forget straightness for a second. I'm telling you that L1 is a line, L2 is a different line, and they intersect at the points A and B. I'm lying. This is an impossible picture. How do I know it's impossible? That's what we need to prove.
I've seen that.
So I'm going to show that this is impossible. I'm going to assume that there's two lines with this that behave this way and show it's impossible based on our assumptions. It violates our postulates. So I'm going to show it's false. So assume by way of contradiction that there exists L1, comma, L2. As a general rule, we will use lowercase letters to represent lines and capital letters to represent points. So I should say lines L1 and L2. I'm often going to skip saying lines or say there are points just because to save time while I'm writing up here. So assume by way of contradiction that there exists lines L1 and L2 such that L1 is not equal to L2. So they're different lines. They're not the same line.
Might know that each time.
That means there exists. Backwards E is there exists. Such that L1 is not equal to L2, and they intersect at points A and B. All right? So we've got two lines that are intersecting, two different lines that intersect at these 2 points A and B. All right.
What
What does that violate up here?
What does that say?
it violates between the lines. It says line 1, line 2.
There exists line 1, comma, line 2. Oh, S dot T dot is such that. I'm going to do that a lot too. Yeah. First couple proofs I write out, there's going to be some hiccups. I'm too used to writing proofs away. I can't change it now. So yes,
So that breaks
keep
line
asking
3,
questions.
because the line contains these two. Wait, no, sorry. Yeah, I think it wrote it wrong.
No, yeah, it contradicts 1-2.
Contradicts 1-2. Observe that 1-2 states that there is only one line. There can only be. Is that way to say that? There can only be one line through A and B. Contradiction.
Through A and B.
Through A and B. So we said, assume by way of contradiction that there exist two different lines that intersect at the points A and B. So A and B are points on line L1, and A and B are points on line L2. Postulate 2 says for any 2 points, there is exactly one line containing them. These are 2 points. So there is only one line I can draw through them. We have 2 lines. There's only one. Contradiction. Therefore, no 2 such lines exist. We said, let's pretend it's possible for 2 lines to go through these points. And we saw it led to contradiction. Right. Because the statement, we could read this as a statement. 2 lines can intersect at more than 1 point. That's a proposition. It's either true or false. Right? We assume it was true, so that led to a contradiction. Therefore, it has to be false. Therefore, there can't be 2 lines that intersect at 2 points. Right?
So what is that? Then,
it's a bad picture. One of these aren't a line. One's a line, one's just some collection of points. One's a curve. They can't both be lines. So whatever they are, they can't both be lines. So 3. Therefore, two lines cannot intersect at more than one point. Maybe they don't intersect at all. We didn't say they have to intersect at a point. We just proved that they can't intersect at more than one point. Because if they intersect at more than one, they intersect at two, and we showed that's impossible. So there's our first theorem. All right, next theorem. There are at least three lines in a plane. Theorem 3-2. There are at least three lines in a plane.
What's your sign by A and B on the second one?
Oh, back and forth arrow. Let me draw that better once. So I draw an arrow pointing this way, and then an arrow pointing back at it. And that's the symbol for contradiction. So you're telling your reader, the sentence you just barely read should be a contradiction. It should contradict what we've already stated. So you're just making it very clear to the reader, something's got to give. So back and forth arrows like that, that's contradiction symbol. All right. So now we want to argue that there are at least three lines in a plane. Nope. So how are we going to argue for the existence of three lines? As a general rule, it's a good idea to get a picture of what you're trying to do first, and then go from there. So I'm trying to argue for the fact that there's three lines in a plane. How can I argue that?
Well,
First, define what you define a plane.
define what a plane is.
We don't have a definition of plane. Plane is one of our undefined terms.
Okay.
These are the only three things I know so far. We'll introduce more postulates in a sec.
Well, so there are at least three non-collinear points.
Perfect. I know that there's 3 points in a plane that aren't all collinear. So there's 3 points, and it's impossible to draw one line through all 3 of them.
It is possible to draw three lines. From A to B, from B to C.
So I can draw this line.
Would a circle be
That's a line.
a line?
No, a circle's not a line. But that's a long ways ahead. We could draw the line that goes through these points, and we could add the line that goes through these points. So in other words, postulate 1 gives me that there's 3 points, and then postulate 2 tells me for any 2 of those points, there's a unique line through those 2 points. There's 3 combinations of the 2 points, therefore, there's 3 lines. That's the logic for the proof. So 1. By 1, there exists 3 non-collinear points in the plane, comma, call them A, B, and C. Okay, 2. By postulate 1, 2, comma, there exists lines through AB, maybe I won't comma separate them. Lines through AB, comma, AC, comma, and BC. Right? 3. Since none of the lines can contain all 3 points, comma, they must be unique. So none of them could have actually been the same line twice. 4. Therefore, there are 3 lines in the plane. Therefore, there are at least 3 lines in the plane. Okay. Not bad?
So the reason they can't be all the same lines is 1-1 says that they can't be.
Yeah, 1-1 says that they're non-collinear, which means they can't all be on the same line. If any 2 of these lines were actually the same line, so if those 2 were the same, or those 2 were the same, or those 2 were the same, then we'd get all 3 points on one line. Which we know that they can't be on one line, because they're non-collinear points. So it means to be non-collinear. Can't all be drawn on one line. So there we go, learning a lot about our geometry so far. Okay, so I get you to your first exercise group. Now, pay attention in the order that you do your exercise groups on your homework, because they're going to ask you questions like, what do we know so far about points? Stuff like that. And when you're doing exercise group 1, you know less things than when you know exercise group 4. Because we've gone further. We're going to introduce new postulates now. So pay attention to the postulates you have for the exercise groups you're doing. Exercise group 1 is the only one where that actually matters. The rest of them doesn't really matter. Okay, let's finish off our postulates, and maybe we'll just now write them over here. So for postulate group 1, we had 1-1, which is the 3 points. We had 1-2, which is, if we have 2 points, then that gives us that we have a line through the 2 points. And for 1-3, we have, if we have a line, that gives us that we have 2 points on the line. Just pictorially draw it out for a quick reference so that we can clear the space there. Okay, now we're going to introduce postulate group. Postulate group 2. Now this is still just a, okay, yes, this is postulate group 2. Shoot, I erased my undefined terms. So undefined terms, I told you for this section, were point, line, plane, and then between. Between is our next postulate, or is our next undefined term. And our next postulate group tells us what it means for two points to be between each other. Now, intuitively, let's think about what it means for between. How would you tell me, using day-to-day language, what it means for one object to be between 2 objects? So you want to say right now that my coffee mug is between us. Is it between us now? No. What changed?
1 point moved.
I moved, and so him, I, and the coffee mug can no longer be contained on a line. Notice that betweenness doesn't make sense unless you can line up the 3 objects. What do we mean by line up the 3 objects? We mean place them on a line. Line them up. So betweenness only makes sense for points when the points can actually be contained on a single line. And then these are the properties that they're going to have. You'll see that they're pretty intuitive. I might keep swinging around. Hate the tie. That can be annoying. Maybe I'll just set it there. All right. So, first postulate group. And I'm going to write between us a funny way, so you ready for this? Here's how we write between us. If A, B, C. The way you read that is if B is between A and C. Strictly speaking, betweenness is a predicate that takes 3 points and spits out true or false. So if we were to write it explicitly, we would have to have our betweenness predicate, and it would take three terms, A, B, and C. And that's how we say betweenness applies to A, B, and C. So strictly speaking, it's a predicate. It's one that we use so much that we don't even want to use its notation for it. We're just going to write it out exactly like that. But it is a predicate, just like we talked about in logic. You give it, it's a predicate that takes three terms. You give it three terms, and it spits out true or false. Okay. So if B is between A and C, is the way you read this. One more note. ABC says the exact same thing as CBA. Those both say B is between A and C. So order does not matter. All that matters is which term is middle term. Okay. So if B is between A and C, then A, B, and C are three distinct points on a line. So if I know that A is between B and C, or if I know B is between A and C, I instantly know that A, B, and C are three distinct points all on the same line. So anyway, betweenness makes sense. 2. Let's get intuition for 2 really quick. So now imagine I got a line here, and I randomly picked 3 points. Maybe this one's A, maybe this one's C, maybe this one's B. Which one's between which ones?
C is between B and A.
C is between B and A. Okay, what if I move them around? What if I love stick my A here, my B here, and my C here?
B is between A and C.
B is between A and C. Is there any way I can arrange those 3 points so that one's not between the other 2? Not unless I say this point is A and B, maybe something like that, and that point C, right? So as long as A, B, and C are 3 distinct points, there's no way I can arrange them so that one's not between the other 2. Okay, so that's what our second postulate says. If A, B, and C are distinct points, comma, then either, and when we say then either, we mean I'm about to use or in the exclusive sense, not the inclusive sense. Then either ABC, comma, BAC, comma, or ACB. And again there, we're saying one and only one of those 3 betweenness relations can hold. We mean that in the exclusive or sense, not the inclusive or sense. Okay? Next postulate. (2-3). Any 4 points, and by that we mean distinct points, any 4 points on a line may be relabeled A1, A2, A3, A4. I should comma separate those. A1, A2, A3, A4, such that the only betweenness relations are A1, A2, A3, comma, A1, A2, A4, comma, A1, A3, A4, comma, A2, A3, A4. All right, let's get intuition for this one. So this one says we've got a line, pick any 4 points on the line you want. They have to be distinct points.
A1, A2, A3, A4.
It says whatever they were named before, we can relabel them. We can rename them. Call them A1, A2, A3, A4.
A2, A4,
A3, A4. You can always relabel them so that these are the only 4 betweenness relations.
In the last one you forgot. Wait, why do you only have 3?
Because
It's a betweenness relation. Betweenness only applies to 3 terms. So, what is between what? Tell me all the betweenness here that you see.
2, 3, 4. Wait.
What is between what? Tell me in words what points are between which points.
Okay, 2 is between 3 and 1.
Between 1 and 4.
Okay, stop. A2 is between A1 and A3. That's one.
A3 is between A2 and A4.
So that's right here. A2 is between A1 and A3.
Oh.
Let's see. A2 is also between A1 and A4. That's right here. A3 is between A1 and A4. That's right here. And A3 is between A2 and A4. That's right here. And those are the only betweenness relations there. We got them all.
Wait. A2 and A3 can't be between A1 and A4 at the same time.
Yeah, but the way you write that is you said, look, you said A2 is between A1 and A4, and A3 is between A1 and A4. So you state them both. But no, you don't just write out big strings of letters saying all these betweenness relations.
Right.
So betweenness is something that applies to 3 points at a time. If you want to say multiple of them hold, you need to explicitly write them all out. Okay. The next postulate is the line extension postulate.
That's the new postulate group, or?
Nope. Still the extension, or still same group, still betweenness. 1-4. Let me get the verbiage on this right. If A and B are points, if A and B are points on a line, then there exists points C and D such that A, C, B, and A, B, D. Let's say pictorially what this tells us. So if I have some point A and some point B on a line, I know 2 things. I know 1, there is going to be a point between them. If you have 2 distinct points, doesn't matter how close they are, I can always find some other point between them. So, if A and B are points on a line, there always exists a point C, such that C is between them somewhere. Furthermore, there always exists a point D, such that D goes beyond B. I can always find a point further down. This is kind of the postulate that says lines are infinitely long.
Right.
I can always find another point. Well, it doesn't quite give us that yet, but I can always find another point further along the line. D. So you have 2 points, you can always find a point between them, and you can always find a point further along from them.
If you have 4 points on the line.
If you have 2 points on line. Once I know that I have 2 points on line, so I know I have these 2 points. If I know that I have those 2 points and they're different points, then this postulate says, you also know that there must be some point between them. So that's saying that if you have 2 distinct points, there's always a point between them, which intuitively we know should be the case.
At least 1 point between them. Can there be multiple points between them?
Yeah, because now look, A and C are 2 points on line. This postulate says there must be a point between them. Okay, now that's 2 points on line. This postulate says there must be a point between them. And the point between them doesn't necessarily mean the middle point. I'm just trying the middle. It just says there must be some point between them.
Okay.
And we can do that indefinitely. So there's an infinite number of points between A and B. Furthermore, we can always extend it further. That's what the second part of the postulate says. It says if I have 2 points on a line, A and B, I can always find a point beyond them, B, such that A, B, D. Now B is between A and B. And now I can reapply that to these two, finding a point that makes E, so that D is between B and E. And I can extend further, and extend further, and extend further. And between us, it doesn't matter which way we write this, so I can also say, extend it this way, and extend it this way, and extend it this way.
So technically, there's infinite points on the line.
Yes, there are infinitely many points on a line. We can now conclude that from this postulate. Well, kind of combining this postulate with our first postulate, or our second one. Our second, was our second one? No, our third one. Our third one says the line has at least 2 points. This one says, now if you have 2 points, you can get infinitely many. So putting those two together are what gives us lines with infinitely many points. Okay. And now before we give our fifth postulate here, we need a definition. Because now we're going to talk about sides of a line. So let's talk intuitively about this for a second. So I've got some line here, L1. You with me?
Yes.
Now the line goes all the way through the plane. Pictorially, that's how we think about it. We're about to, this is going to be the postulate that tells us it goes on forever. So here's a line on the plane, in the plane. Notice that the line is going to split the plane into 3 sets. There's going to be all the points on this side of the line, the point A. Then there's a point actually on the line. And then there's all the points on this side of the line over here, set B. Maybe use X and Y for sets, and then the points at the start of the alphabet for points. So a line divides the plane into 2 sides. That's what our fifth postulate is essentially going to say. We just need to come up with a definition to make it clear what we mean by a side of the line. So here's where our definition is going to be. For sides of the line, and then we'll write out our fifth postulate. Maybe do this. Maybe we'll have enough space that we can do our proofs over there. So definition. This is definition. Oh, I didn't put the number next to it. Not sure which one it is. This is our first definition, right?
Yeah.
Okay, so then let's give you definition 3.1. So now we got our first definition in the class. So I told you we have 4 things in every axiomatic system. We have undefined terms. So far, what were our undefined terms? Points, lines, planes, and betweenness.
Right.
We have postulates or axioms, same thing. Here's all our postulates or axioms so far. We've already proved a couple theorems. Here's an example of a theorem. Now we get our first definition. And with that, you've seen the 4 components of every axiomatic system. From there on out, we just come up with more definitions and prove new theorems. That's it. And introduce new postulates along the way as we need them. But you've seen all 4 points. And this is what every axiomatic system is. Whether you're talking about geometry, you're talking about real analysis, calculus, whatever it is. Every field of math is just an axiomatic system, just like this. That's why geometry is so important. Get you competent in one axiomatic system, and that's the same thinking in every other one. Anyway, so our first definition here, we're going to define what it means for 2 points to be on the same side of the line. So I have some line L1 here, and I have A over here, and I have B over here.
Why can't you do postulate 5?
Postulate 5 is going to use this definition. So we got to do our definition first for what it means for points to be on the same side of the line. Are A and B on the same side of the line?
No.
Intuitively, how do you know that?
Because the line's
Because the line is between them. Or in other words, to be a little bit more precisely, there's a point on the line between them. There exists some point C on the line between A and B.
Where the two lines intersect.
We don't even need to go any further than that. There exists a point on the line C between A and B. That already means that, yes, if you were to draw a line through A and B, it would intersect at C. Because if you have 3 points between each other, then that means there's a line containing those 3 points. If B is between A and C, then A, B, and C are 3 distinct points on a line. So your intuition is right, but exactly what he said is going to be almost verbatim what it means for points to be on the same side. So now let's try out the definition. And, no, well, I'll just try it out. As I said. 2 points not on a line L are said to be on opposite sides Two points not on line L are said to be on the same side of L. Oh. We define it on the same side. 2 points not on line L. So let's intuitively think about how I'm going to say this. So how do I know if 2 points A and B are not on the same side of line L?
There's not, L's not in between.
Yeah, there's no point of L between them. So 2 points not on a line L are said to be on the same side of L, provided that there is no point on L between them.
Oh, I see.
Between them, comma, I guess would be both, and are on opposite sides if there is a point between them. These definitions, by the way, are in the book. I'm kind of just spitballing them. And they're on opposite sides if there's a point on L between them. Okay, pretty intuitive. You would have almost guessed that definition word for word. You basically did. So now, our fifth postulate. And our last postulate for the chapter. Postulate 2.5 says,
Did we do postulates for chapter 2?
no, this is when we're finally starting geometry.
Actually, not.
All right, this says each line separates the point not on the line into two sets into two sets. If 2 points are in the same set, are in the same set, comma, they are on the same side of the line. And if they're in different sets, then they're on opposite sides of the line. We'll bother writing that down. So those are the end of our postulates for this chapter. Not too bad, right?
What I mean by sets is not like coordinate points.
We mean sets just like sets from set theory. That's why I always like to start with logic and a quick set theory first, show you all the foundations. We're allowed to use sets in describing these things, and we're allowed to use logic in describing these things. And so it's understood that a plane is a set of points, and a line is a subset of the plane, if the line's in the plane. So a line separates the plane into three sets. Essentially, this says, look, a line splits plane in three sets. You have the line itself, then you have all the points on one side of the line, and all the points in the plane on the other side of the line. And if 2 points are in this set, then they're on one side, then they're on the same side. If 2 points are on this set, then they're on the same side. If a point comes from either set, then they're on opposite sides. So yeah, we can now refer to the sides of the lines
So what
as
about
sets.
points on the line?
So this is about the points not on the line into two sets. So in general, it's saying that there's three sets. There's a point on one side, there's a point on the other side, and then there's a point actually on the line. And the entire plane can be split into those three sets. If you ignore the points on line, okay, then we split into two sets. Okay. All right, next definition. Definition of a line segment. Intuitively, what do we mean by a line segment? A line segment, pictorially, looks like this, starting from some point A and ending at some point B.
Right.
So, what are all those points? What are all these points? Tell me in words what all those points are.
Are the points on line AB?
Notice that this is not a point on the segment. It's on the line through A and B. The line through A and B goes on forever. We're talking about a line segment. We're talking about just these points. Which points are those points? Tell me in words. A and B are some of the points, but we're including this point, aren't we?
Yeah. There's infinite, that's what I'm saying.
All right, so what are all those infinite points? Which infinite points are they?
They're in between A and B.
All the points between A and B. So a line segment AB is the points A and B, and all the points between A and B. Perfect. Yeah, simple definition of a line segment. Notice how when we create our definitions, we have to refer to our undefined terms. When I created the definition of a line segment, I had to refer to points and between. Two undefined terms. So I defined a line segment in terms of points and between. All right, next definition. I think we're on another definition. Maybe it's a theorem. Definition 3.3. Okay, so now we get definition of a triangle. If A, B, and C are non-collinear, comma, then triangle, the way we talk about triangle in geometry, you'll get used to this notation. We draw a little triangle, and then we do ABC. Then the triangle ABC consists of, what does it consist of? You tell me the definition. We have three non-collinear points. We're going to call them A, B, and C.
It consists of
And we're coming
lines
up.
B, A, AC, and CB.
Consists of the line segments A, B, B, C, and AC. Perfect. So then triangle ABC consists of the line segments AB, comma, BC, comma, AC. Notice that a triangle is only the edge of the shape. Sometimes people think of a point like this as a point on the triangle. That is not a point on the triangle.
Point in the triangle.
We'll get to interior, and that will be another definition. But yes, so just to be clear, that is not a point on the triangle. The triangle is just these actual three segments. We call the points. What do we call the points A, B, and C? You might have heard the word before.
Point.
You know which points we call the points.
On the triangle.
Yeah, we call the points A, B, and C. I guess I'll listen. The vertices.
Oh, right.
Of the and the singular for that is sometimes vertices, sometimes vertex. Okay, so now we know what a triangle is. Isn't that nice? All right, and then that gets us to exercise group 3-2. Now, 3-2 is a pane. Big exercise group, pane. You only have to do 3 of the proofs. So you can pick whichever 3 proofs seem the most fun to you. I won't make you do more than 3 proofs per exercise group. I don't care which 3 you do, pick whichever ones you want. You can do more than 3 if you want, but you only have to do 3. Because it can become pretty time consuming to come up with how to prove all these.
Okay, so how many
3-2?
exercises are in?
So for every exercise,
A bunch of the exercises are not proofs. Some of them just say, list all the betweenness relations between these 3 points. Okay, that's easy. So you can do all the ones that aren't proofs, those will be easy. Some of them will say, prove this, prove that, prove the other.
So for the proofs, you only have to do 3.
Yeah, so you only have to pick 3 of them. So 2 is a proof, 9 is a proof.
2 is proof. Is it 4 proof?
4?
No.
No. 12 is a proof, 13 is a proof, 14 is a proof, 15 is a proof, 16 is a proof, 17 is a proof, 18 is a proof. So there's a lot of proofs.
15, 16, 17 are all
so
proofs.
we only have,
So per section, you only have to do 3 proofs. So if the problem says prove da 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 da, then that's a proof problem. You only have to do 3 of the proof problems. So do all the problems that aren't proofs, because typically a problem that's not a proof, it's typically a problem that's just trying to stretch your intuition. So I want you to go through all the stretch your intuition type problems, because that will help you with your proofs down the road. But when it comes to actually proving things, it takes a bit. And if you ever get stuck on a proof,
There's a lot of extra credit on 3-2.
yeah, 3-2. 3-2 was the hardest homework section in this chapter. 3-2 and then
chapter
3-6.
3.
Yeah, chapter 3. I don't know the book yet. I'm only done with chapter 3.
Oh,
I'm just saying a chapter ahead of you guys.
oh, I see. Did you do all of this?
Yes, I did. So,
I actually appreciate
as much homework as you guys have, I always have the same amount of homework, and then some. Because I don't have an answer key for this book. But I will next year, and that'll be nice.
making it right now.
Yeah, I'm making it right now.
This is the first time you taught this class.
Technically, I taught geometry once before.
It wasn't.
But this is the first time I'm teaching this class like this, yeah. Okay, so now we move on to the next section. Hopefully I'm not skipping anything.
What is 3-3?
3-3.
Exercise 3-3. Oh, I guess it's exercise, so we don't even do that.
Also, if it says restate this in your own words, you can always skip those ones.
Okay. Wait, if it says what?
Restate this in your own words, you can always skip those ones. Or come up with your own examples for this, you can always skip those ones. And we'll always just give you full credit on those. I don't think there's much value in them. Okay. So moving on. Next, now we have theorem 3-3. So on to the next section. Let O be any point on a line L, then the points of L different from O are divided into 2 sets. such that one, P and Q are in the same set, then we have that. Okay. So maybe we'll write up what we're trying to prove, and then we'll prove it. Theorem, I think this is 3-3. Is a point on line L, comma, then the points of L different from O. From O can be divided There's a teacher's chair in here.
I'm pretty sure they took one from this room and put it down. The spirit labs, Mr. Joseph. Okay.
I like how we rob from one teacher to give to another. Can be divided
Good job, you will find one.
now into two sets such that one, if P and Q are in the same set, if P, Q are in the same set, then we have either, so one and only one of these two, P, Q, O, well, let's do the O first, O, P, Q, or O, Q, P, 2, if P, Q are from different sets, then we have the O, Q. All right, so that's what we're proving. Let's pictorially draw this out. So we're saying if we've got some line L here, and we've got some point on the line, call it O, then O divides the points on the line that aren't O into two sets, the two sides of the line, obviously.
Right.
Now, if 2 points come from the same side, so if P and Q are both over here, then we must either have Q is between P and O, or if P and Q are both over here, this point could have been P, this one could have been Q. And in that case, we would have had P is between Q and O. So if P and Q are on the same side, then you must either have P is between O and Q, or Q is between O and P. And then if P and Q are on different sides, doesn't matter which one's on which side,
Then O is going to be in between.
then O is going to be in between P and Q. Okay? That's what we're proving. So that's our proof of it. Okay, so let's start by getting our line. So let's go over pictorially how we're going to come up with this. So I'm going to start out with the line. I'm going to start out with O on the line, right? How am I going to go about this? I basically want to divide this line L into two sides. How am I going to do that?
By putting a point on it.
How do I know? We're proving that putting a point on it can divide it. That's what we're proving.
Okay, we know it because
What do we know divides things into two sides?
having something in between them.
We know that a line can separate things into two sides.
So you'd say that a line goes through point O.
So I need to, first off, pick some point not on L. Doesn't matter. Some random point not on L. How do I know that there's a point out here not on this line?
Because of theorem I1.
Because of our very first postulate. There's 3 non-collinear points in the plane. So our first postulate tells me that there has to be some point A out here where A is not on the line. And so now I have this point O and this point A. What am I going to do with those 2 points?
Big line.
Make a line. Which postulate am I using to do that?
I2.
Postulate 2. Postulate 1, 2. You have 2 points, then there's a line that goes through those 2 points. That's our second postulate, right? And now this new line, we'll call it M. What does M do? We know that M can divide the plane into 2 sides. Using this. A line separates the plane into 2 sides. So M separates the plane into 2 sides. We have all the points on one side of the plane. We'll call those points big X. We have all the points on the other side of the plane. We'll call those points big Y. Notice that L has some points in big X, and L has some points in big Y. So L has some points on this side, and L has some points on this side. So we just really split the line L into 2 sides.
Right.
That's the logic. We follow all that? Let's reconstruct it one more time. What are we saying? We say start out with some line L and O. I want to divide this line into 2 sides. Into 2 sets. How do I do that?
You can do that with a
I
line.
need to get a line through O, so I'll find some A out here, and that's just to give me my line. There we go. Now I know this new line M divides the plane into 2 sides. I didn't want to use line L to divide line L, because no points on line L are on either side of line L. I need a new line to divide line L. So M is the line I'm using to cut line L into 2 halves. Now, a bunch of points over here, we'll call the points over here L sub 1, and the points over here L sub 2. The points L sub 1 are on one side, the points L sub 2 are on the other side. And any points in L2, if I take a point from L1 and L2, PQ, like this, then O is going to be on this line between them. And if I grab them on the same side, then we'll have the betweenness relations that we know, or that we're looking for. But that's pictorially what we're going to do. So probably shouldn't erase that picture. Just draw a scribble picture down here for that. So we're going to have L like this. We're going to have O a point on there. I'm going to take some A out here. Give me some line, we'll call it M, which will divide it into the 2 sets X and Y. And then we'll go from there. So let O be a point on line L, comma, and by postulate 1, 1, comma, there exists A such that A is not on L. So we got our point A out here. For sure, A is not on L. That's what we know about A. So 2, by postulate 1, 2, comma, there exists line M through A and O. Three, by postulate 2, 5, M divides the plane into 2 sides, comma, call them the set X and the set Y. So now X and Y are either sides of little m there. So, of the line L here, notice that O is the only point on the line M.
That's right.
So all the other points on L have to be on one side. They either have to be in set X or set Y. O is the only point that can be in line M. How do I know that? How do I know that if I grab some random point on L, call it P, that P can also be on M?
Because O's on M, and it's a different line than O. It's a different point.
Because O's on M, and two lines can only intersect at one point. So M can't be another point on, or P can't be another point on.
If you have O right here and P right here, is that one point?
It's a picture. The only way for P to be a point different from O, let me say this differently. If P is a point separate from O on line L, then P can't be on line M.
Right, I understand that. I'm just saying, apart from that, if P is like right on top of O, is that considered the same point? Or is that considered an
We're
intersection?
doing a drawing. Maybe there will be a drawing where I do, okay, here's O and here's P, and I do my drawing, and I say, those are two really close points that you can't see the distance between them. Other times I might say, let's consider the point, and it's O and it's P. And that's two names for the same point. So as long as P is a point separate from O, then we know that P cannot be on line M. O is the only point that's on both L and M. So if I grab some other point P on the line L, it cannot also be on M. Because then otherwise M would intersect L at 2 points, which is impossible. So 4. Let P and Q be points on L such that P is not equal to Q is not equal to O. So we have 3 distinct points. No 2 points are equal to each other. Good?
Yeah.
Okay. So I grabbed 2 random points on here. We don't know which points we grabbed. I'm just throwing them in the picture just because. Let's see. First, we're going to handle where they're on the same side, so we'll draw that case first. Here's O. Since M already intersects L at O, comma, then neither P or Q can be on M. Then neither P or Q can be on M, comma, and so have to be in the sides of M. And so have to be on a side of M. So if I pick 2 other points, P and Q on the line L, they have to be either on one side of M or on the other side of M. Okay, so now we have 2 cases. 6. Then either P and Q come from the same side, or they come from different sides. Or different sides. And we need to show that if they come from the same side, this happens, and if they come from different sides, this happens. Okay, so let's handle first the case where P and Q come from the same side. If P and Q are on the same side of M, maybe remind you that we're talking about sides of M here. What do we know for 2? What does it mean for 2 points to be on the same side of M? What does it mean for 2 points to be on the same side of a line? What does it mean for these 2 points to be on the same side of M?
They're in a set.
They are.
What exactly does it mean for 2 points to be on the same side of a line?
It makes it rain.
There's no point in between them.
There's no point on the line between them.
Yeah.
That's what it means. So if P and Q are on the same side of line M, then there can be no point on M between P and Q. So if P and Q are on the same side of M,
Or not, or can't you just say line M does not intersect? Would not intersect Q and P.
well, what are we, don't lose track of what we're trying to show. I'm trying to prove that if P and Q are on the same side, then we either have this between us relation or this between us relation. That's what I'm proving. And I'm going to show that if they're on different sides, we have this between us relation. So I want this in terms of their between us relation. So if P and Q are on the same side of M, then O cannot be between P and Q. Then O can, maybe I'll just spell it out. Here's what I was going to write. Maybe you're okay with this. O between P and Q is false. It can't be true. O can't be between P and Q. Maybe that's too confusing.
No,
No, I got that.
Okay. You guys weren't responding fast enough. Then O is not between P and Q. Okay, so I know O isn't between P and Q. I know O, P, and Q are all points on L, and I know that O is not between them.
Right.
I'm trying to get to, what am I trying to show? I'm trying to show that OPQ or OQP. That's what I'm trying to show. So I know that O, P, and Q are 3 points on line. They're all on line L. And I know that O is not between P and Q.
Right.
Okay, now what?
Which means you can have OPQ or
How do you know? How do I know I can have these?
because they're not in between them.
If you're going to justify something, you need to justify it from a postulate or a previous theorem.
Because of line 7.
Because of what?
I'm saying line 7 in your theorem. Proved it on line 7.
Line 7, okay, so I know that line 7 tells me that POQ equals false. Okay, I know that. I'm trying to tell either this is true or this is true. I know this is false, okay. I need that this is true or this is true. Two.
Theorem 2.
Ah, postulate 2-2.
they're possible.
Genius. If A, B, and C are distinct points on a line, sorry. Sorry about that. Point on a line. Doesn't make sense to talk about between us if they're not on a line. If A, B, and C are distinct points on a line, then either B is between A and C, A is between B and C, or C is between A and B. All right, I know that O, P, and Q are 3 distinct points on a line. So what do I know?
That it can either be those things.
I know it can be OPQ, or it can be PQO. Let's see, it can be OPQ, OQP, or it can be POQ.
Right, we know it's not OQP. Because of line 7.
Oops, that was an O. So it has to be one of these 3. Line 7 says it can't be this one.
No, it can't be in the middle.
No, it can't be where O's in the middle.
Oh, right.
Can't be where O's in the middle. And so it has to be this or this.
Or PQO.
PQO?
Yeah.
Remember, it doesn't matter if you write OQP or PQO, they'll say the same thing. They'll both say Q is between O and P. So here's PQO. It's the same thing as OQP. OPQ is the same thing as QPO. So either P is between O and Q or Q is between O and P.
Those are the two options. Either
Those
way,
are the only two
O is
options.
not in between.
So 8. Then by 2, we have OQP or OPQ. Okay, so we handled that case. So I showed if they're on opposite sides, then we have one of these two betweenness relations. Okay, now let's handle the case where they're on the opposite sides. So now we need to handle the case where P is over here, but Q is on the opposite side. So if P and Q are on opposite or different sides, I don't know why I always say opposite, but I do. Opposite sides of M, then what?
Then they have O in the middle of them.
Then there must be a point on M between them.
Right, and that point is O.
And that point has to be O because that's the only point where M intersects L. So then, there has to be a point on M between them, comma, and that point has to be O. Because if there's a point other than O, then M would intersect L in 2 points.
Which is probably impossible.
Which would be impossible. So 10. So then we have POQ. And we're done. That's what we were after. So we showed if this was the case, then we have OPQ or we have OQP. And we showed that if this was the case, then we have POQ. Cool little theorem. All right, on to the next one. Next definition. Two sets, X and Y. Oh, it's just a definition about that theorem. Definition, oh shoot, I forgot the number. This is our third definition?
3, 4.
3, 4? 3, 4. Okay, pick your next one.
Is it a big definition?
So I don't actually skip one. Definition 3, 4. The sets X and Y above are the sides of a line on the side of L. Let's leave it at that. In other words, now we can talk about splitting a line into two sides. And now what do we know about the sides of a line L? If 2 points are on the same side of a point O on line L, then we have this. If 2 points are on opposite sides of a point O on line L, we have this. So the sets X and Y are the sides.
What's that arrow right there by the Y? What's that saying?
Point O on line L. That's going to be really easy. I'm saying the sets X and Y that we've named up here. I could have said the sets X and Y stated in theorem 3-3 or whatever. That's why using the author's definitions is probably superior. Okay, next definition. Definition of array. Pictorially, what is array?
Array is the one ending line.
So
It's the line that goes on forever one way, right?
here's some line. Pick a point on the line, we'll call that point O. Array is all the points on one side of O, including the point O. So let O on line L, comma, then how do I state it? That's much early. Array from O. Array from point O is the point together with all the points on a side of O, together with all the points on a side of O, of a line L through O, of a line L through O. So in other words, pick a point O, draw any line through O that you want, pick a side, and that defines array. Okay, so now we have the definition of array. Next definition. The set of all points on two rays from a point. Oh, we're talking about the definition of an angle. Okay, so definition of an angle, let's get it pictorially really quick. So an angle is defined as two rays. And it has to be two distinct rays coming from a single point. So here's a point O. We have one ray coming from the point O, and then a different ray coming from the point O. I can't draw another ray on the same point, otherwise it's not an angle. So an angle is two rays from a single point.
Right.
I'm going to draw a point. Is that a point in the angle?
Yes.
No.
No.
The angle is just the rays.
Okay.
That is not a part of the angle. The same way that when I have a triangle, this point is not a part of the triangle. And now you know why a triangle is called a triangle. It's an intersection of three angles. So I agree to call that. So a point inside here is not part of the angle. Sometimes we draw a line like this to show the two rays that are connected in the same angle. Because sometimes we draw angles on top of angles. So you've probably seen before in your life pictures like this, where we have two angles drawn on top of each other, and we say we're talking about, we could say we're talking about this angle and this angle, so we might draw lines like that. Or maybe we were talking about this angle, this ray together with that ray makes an angle. So that's the point of those lines, is to show you the two sides, the two rays associated with the angle. Since we draw angles on top of each other so much, this is very common notation. But sometimes that makes kids think that, oh, so this point right here is inside this angle. No. We will talk about the interior of an angle, and it will be in the interior of an angle. So with that intuition for angles, let's draw out now its actual definition. The set of all right, definition, this is 3-6.
How many definitions are there
In the book?
that in this section?
11. All right, definition 3-6. The set of all points on two rays from a point O. The set of all points on two rays from a point O is an angle. So point O is the vertex. Call that the vertex of the angle. If A and B are points on either ray, neither of them O, so not O, then we call the angle AOB. Or we can always just call it just angle O if we want. So what are we saying? Here's O, here's a point A on the ray, one ray, here's a point B on the other ray. We might name this angle AOB, or if it's obvious that there's no other angle at the point O, then sometimes we just call it angle O. So when I have a triangle like this, ABC, it's very common to refer to that angle right there as just angle A, not necessarily angle CAB or angle BAC, but you could use either. So both those are valid notations for talking about angles. Let's see. And then if the two rays lie on the same line, we call it a straight angle. If the two rays lie on a single line, we call angle O a straight angle. So what's a straight angle? Here's one ray, here's the other ray, they lie on a line. Straight angle. Still an angle out. It's two rays joined at one point. Any questions on that one? All right, next definition. I'm not going to write out, I'm just going to write a picture for it. Definition 3.7. What it means for angles to be vertical angles. So when you have two lines intersect at a point, then we call these two angles vertical angles, and we call these two angles vertical angles. Being vertical is a relation between two angles. It doesn't make sense to call one angle a vertical angle. Two angles together make vertical angles. These two are vertical angles, these two are vertical angles. Make sense?
The vertical because they're 90 degrees or what?
It's just a name. They're vertical angles. They're in some sense on opposite sides from each other.
I'm saying one is vertical to 2.
One is a vertical angle to 2. The right way to say it is 1 and 2 are vertical angles. 3 and 4 are vertical angles.
Okay.
Similarly, we could have had a picture like this. In this case, this angle is vertical to that angle.
Right.
This angle is vertical to this angle. Okay, so that's what we mean by vertical angles. You don't want to try explaining all that in words. All right, definition 3.8. It's what we mean by adjacent angles. Here's another one I'm not going to write out. Definition 3.8. What we mean by adjacent angles. What do we mean by adjacent angles? It's two angles that share a ray. So they both have this ray in common. And then they have their other rays not in common. So they have a ray in common. Their other rays are not in common. And their other rays are on opposite sides of the line through their shared ray.
Well, that's an adjacent angle.
This angle is adjacent to this angle.
They're next to each other.
Now imagine that I was talking about this angle and this angle. These angles are not adjacent anymore. They have a ray in common, but their other ray is not on opposite sides of the line through the given ray.
Go back. Yeah.
All right. I'll read the definition to you once. Well, let's draw the picture and then I think you'll get it. So this angle and this angle are adjacent. Let me read the precise definition. If two rays have a common vertex, here's O.
Right.
Two rays have a common vertex. If two rays have a common vertex, a common side on line L. So here's O. So they have the vertex and they have a common side on line L. So the side, I said two rays there, that should be two angles. If two angles have a common vertex and they have a common side on line L, so this side, that ray, is on line L, and their other sides are on opposite sides of line L, and the other sides of the angles are on opposite sides of line L, then the two angles are adjacent. So these are adjacent angles. These would not be adjacent angles. Here's O. Here's a ray, here's a ray, here's a ray. This angle together with this angle. Notice that these angles have a common side. This ray called R1. Both angles have R1 in common. But if we look at the line through R1, the other side of both the angles do not come out on opposite sides of the line L1. The other arms are on the same side of L. L, since that's what we call it here. Up here, notice that the other arms are on opposite sides of L.
Okay.
So these are adjacent angles. These are not adjacent angles. Because this other side are not on opposite sides of the line through the common ray. Well, this one here is R1.
If L was between the middle one, then they would be adjacent.
If this was the ray that they shared. They don't share this ray. They share this one. Over here, I'm talking about this angle and this angle. The only side they have in common is this one. So the line through their shared side is the line that we're talking about. And notice that the other sides of the angles aren't on opposite sides of the line through their shared side. Here it is. Here we're talking about this angle and this angle. So their shared side is right there. Here's the line through their shared side. Notice that their other sides are on opposite sides of the line. Some of these definitions, what seems kind of obvious in picture, it's actually kind of technical when you state it out explicitly.
Right.
Okay. If the non-common sides of two adjacent angles form a straight angle, then we call them supplementary. So here I accidentally drew supplementary angles. Let's pretend that that was something like that. Okay, those are still adjacent angles. So definition, so write what we're defining up here. These are adjacent angles. And then definition 3.9.
You just said that's not adjacent. You said that it's adjacent if they both.
That's
straight line.
adjacent.
They were really neat.
This one's adjacent.
Okay, so
They share a common ray,
And the common ray divides the common angle.
and the common ray, the line through the common ray, divides the other sides. Whereas the picture we had before, like this and like this, Now those are not adjacent angles. Their common ray is right here, and the line through their common ray, sorry, that was a bad line. The line through the common ray, this line, does not divide their other two sides of the angle.
Right.
Okay.
That makes some sense. I never understood this.
All right, so now supplementary. You probably already know these. What are supplementary angles?
They're the same.
Okay,
Is that wrong?
yeah. Supplementary angles are two angles,
That equal 180 when added together.
not 180, a straight angle.
Which is 180, correct?
We haven't even talked about degrees yet. 180 degrees, and not a thought in our heads. And when we get there, we may as well talk about it as pi radians and forget all this degree nonsense. But yes, you've got the right idea. But the definition of a supplementary angles are two angles who together form a straight angle. So you take two adjacent angles, and their opposite rays form a straight angle.
Okay, without the 180 degrees, how do you know something's straight angle?
We have a definition of a straight angle. The two rays lie on a single line. That's what we mean by straight.
Yeah.
So now let me read precisely what it means for two adjacent angles to be supplementary. Two adjacent angles are supplementary if the non-common sides, so this side and this side, the non-common sides, here's our common side, if the non-common sides of the two adjacent angles form a straight angle.
Right.
So the non-common sides form a straight angle, then the two angles are supplementary to each other. Good? All right, and that gets us to exercise group 3-3. It's super easy.
It's not a group though, is it? Is it just a single exercise?
3-3 is a single exercise, so it's not an exercise group. And then 3-4 comes after that, which is also real easy. And then 3-5 comes right after that, which is also real easy.
3-6.
Nope, then we get definition 3-10. What do we want to erase? I really wish I had more whiteboard space.
This side?
Very blackboard.
We kind of referenced the postulates a lot. How good can I draw on that?
We're really bad.
It's not awful. All right. Try it. And so we can look at those and reference them as needed.
Might want to take your mic.
Yeah. Good thinking.
Good book for that mistakes.
What classroom do you teach your topology class?
We're in 5.
For my next one, right?
Oh, good enough. All right. So we'll move over there. Grab my mic. Maybe you can clip it on. Yeah, they keep changing the room I'm in and always sticking me in smaller and smaller rooms. Real annoying. All right. So definition now.
310.
310, thank you. So definition 310.
And then are we just doing homework after this? Or like checking it?
I don't know.
Or is there more stuff? Right. Huh?
Consider a non-straight angle. Consider a non-straight angle with vertex O comma and whose rays R1, R2 lie on lines L1 and L2. Okay, we're getting ready to define the interior of an angle. This is a marker eraser. Really? That works. Okay. Let's draw a picture really quick over here of what we're talking about. So here's O, here's R1, here's R2. And then we've got L1, and we've got L2. Here's O. We're defining the interior of the angle. In other words, we want this point to be a point inside the angle, and this point to be a point in the interior of the angle, and we want this point to be a point in the exterior of the angle. Now notice how we start by saying we can't have a straight angle. Why don't we want a straight angle?
Because there's no.
Yeah, what's the interior of that angle? Right? We don't want to have a definition that talks about that as having an interior. This side is just as valid for the interior as this side. There's no reason to prefer one side over the other. So, we're talking about the interior of this angle. Now, try to tell me where this point is. Just referencing things on this picture.
It's between ray 1 and ray 2.
No, because it's in between a point on ray 1 and a point on ray 2.
So the way we have these rays drawn is kind of an accident, because we could have just as easily had the rays look something like this. So this could have been ray 1. Here's O. And then this is L1.
What is this defining?
The interior of the angle. So I want you to tell me where that point is.
Is on a point. Is in between a point on ray 1 and a point on ray 2.
There's a point on ray 1 and ray 2 such that it's between them?
Yes. No. 100%.
You can't draw a line.
Yeah, that is going to be the case. That's one way to say it. Here's how we are going to say it. It is on the same side of L2 as R1.
Wait.
Here's the line L2.
Okay.
Which side of the line is it on?
Opposite side of L2.
It's on the same side as R1. Here's the line L2. Goes all the way through, right? Line L2 is this. Divides the whole plane. This point is on one of the sides of L2. Which side is it on? It's on the same side as ray 1.
And ray 2.
It's on the same side of line 2. Ray 2 lies on line 2. Ray 2 is not on the side of line 2.
On line.
I know, you're jumping ahead. So here's line 2. The point lies on the same side of line 2 as ray R1. And it lies on the same side of line 1 as ray R2. And that's how we're going to find the interior. And notice that we're defining it in terms of things we already have defined over there. So then, a point P is in the interior of angle O if and only if it is on the same side of L1 as R2, comma, and the same side of L2 as R1. That's what we mean by the interior. It's in the exterior if and only if it's not in the interior, comma, and it doesn't lie on the angle. And it doesn't lie on the angle O. So basically, if you pick a point P, it has to be one of three things. It has to be in the interior of angle O, it has to lie on angle O, or it has to be in the exterior of angle O. By definition. Any questions on that definition? That's going to be the hardest definition in this section. Yeah, it's a mouthful. And it's not all obvious what it is. All right, so our next theorem now, theorem 3-4. Let's see what this one says. If P and Q lie in the interior of angle O, so does segment PQ. Okay. If P and Q,
What is that? What's that? I mean, that definition says ifs in the exterior. If it, what is it supposed to say?
oh, sorry. Where are we on?
Middle. It's the if. Right, yeah.
It's
It's in
IT apostrophe S.
Okay.
It is in the exterior if and only if. It is not in the interior, and it doesn't lie on angle O.
Oh, that's fine.
Yeah, that's fine. If PQ lie in the interior of angle O, comma, so does the segment, by that I mean line segment, PQ. So what this means is, pick any point P in the interior we want, pick any point Q in the interior we want, then the whole segment PQ has to be in the interior.
Back to that definition. Yeah. So when it's referring to angle O, is that referring to ray R1 and ray R2 as well?
Yes. Angle O is this ray union together with this ray.
Nice.
So using some of our set theoretical notation, this is perfectly valid. Angle O is equal to R1 union together with R2. Union those two rays, that's exactly what angle O is. And yeah, sometimes it's helpful to think about them in terms of their set definitions. What exactly the set is. Okay, so let's see, let's prove this. So 1, let PQ be points in the interior of angle O. So our picture could look something like that. Now I instantly know that angle O is not a straight angle. How do I know that angle O is not a straight angle?
You have your two rays.
Because there has to
No.
because it has to be an interior.
Because it has an interior. If an angle has an interior, it can't be a straight angle. So if I have points in the interior of an angle, I instantly know my angle is not a straight angle. Good. Okay. Now I'm trying to prove that 2. Observe that by definition of interior, comma, P and Q lie on the same side of both. Oh, I don't have my lines named. Shoot. Let PQ be points in the interior of angle O. I'm just going to reference my picture there. Sorry, I should have brought this out explicitly. The same side of, the P and Q lie on the same side of, oh, I know how to say this. The lines L1, comma L2 containing the sides of the angle R1 and R2. Okay, I got everything labeled. We call the sides of the angle R1 and R2. L1 is the line through R1, L2 is the line through R2, and so now we have this picture set up. Okay. Now I'm trying to prove that the whole segment, PQ, lies also inside the interior. How am I going to prove that the whole segment does? What is the line segment PQ? Tell me in words what segment PQ is.
Q is a line.
It's all the points, so it's P and Q, and what other points?
All points.
And all the points between P and Q. So I need to show that any point you choose between P and Q is also in the interior. If I do that, then we're done. So I'm going to say,
Point R is.
I'm just going to pick A, but yeah. So let A be any point. A be any point such that P, A, Q. Let A be any point between P and Q. I'm going to prove that A is also in the interior. Assume I want to assume by way of contradiction. How do I want to deal with? Is it not on one of? All right, we'll just handle it. Okay, so assume by way of contradiction that A is not in the interior. Then what do we know? If A is not in the interior, then it is either on, so the interior is all the points on the same side of L1 as R2, and on the same side of L2 as R1. If A isn't in the interior, then it's either not on the same side of this line, or it's not on the same side of this line.
That's by way of contradiction, right?
Yeah, we're assuming by way of contradiction. So we know, ultimately we know A is going to be in the interior. I'm assuming by way of contradiction A is not in the interior. What is the interior? It's all the points on this side of line 2 and on this side of line 1. That's the interior. So if A is not in the interior, then it's either not on this side of line 2 or it's not on this side of line 1. So 5. then A is on the opposite side.
By way of contradiction, A is not on the interior.
By way of contradiction, assume that A is not in the interior. So we know A is in the interior. I'm going to assume by way of contradiction that's not in the interior, so maybe it's somewhere out here. And I'm going to show that's impossible. Therefore, it has to be in the interior. Okay, so assume by way of contradiction that A is not in the interior. Then A is on the opposite side of one of the lines. Maybe both. It could be down here. But it's on the opposite side of at least one of the lines. One of the lines. Call the line, what do we do in our picture? Call it L1. Comma, as P and Q. So if A is not in the interior, then it has to be on the opposite side of one of these lines. Maybe both, but on the opposite side of one of these lines, as P and Q.
As P and Q?
Yeah, it has to be on the opposite side of the lines, as P and Q, the opposite side of the one that P and Q are on.
That's a little bit.
Then A is on the opposite side of one of the lines, call it L1, as P and Q.
Oh, okay.
So we're calling the line that's on the opposite side of L1.
I thought we were trying to prove that A is between P and Q.
No, we picked some point A between P and Q. We're trying to show it's in the interior of the angle. So pictorially, this makes obvious sense to us. This is something, we're being very precise here. Euclid, he wouldn't even prove something like this. He would just look at the picture, think it was good enough, and go on his merry way. But as you're going to hear, if you take math classes in the future, over and over again, pictures lie, pictures lie, pictures lie. You can't rely on pictures. They help your intuition, but when it's all said and done, someone should be able to read your proof without ever looking at a picture and follow it all the way through and say, yes, that follows. So, if A is not on the interior, then it has to be either on the opposite side of line 1 or line 2. Right? And whichever one it's on the opposite side of, we'll call line 1. What if it was really on the opposite side of line 2? Relabel everything and recall L2 L1 and L1 L2. We're fine. So we're going to call the lines on the opposite side of L1. 6. Then what do I know? If A is on the opposite side of L1 as P, then what do I know? What does it mean for A and P to be on the opposite sides of L1?
L1 intersects line A and P.
Which means that there has to be a point on L1 between them.
Oh.
Right?
Right.
So then there has to be a point on L1. We'll call it R between A and P. And similarly, there has to be a point on L1 between A and Q. We'll call that one R prime. You with me? So then, there must exist R and R prime on L1 such that A, R, P, and I'm going to say PAR. Doesn't matter which way we say it. I just think this will be better. PAR.
R prime was that. Like the one on top of it.
Oh, a prime? It's an apostrophe.
What does it mean?
It just means it's another letter. R prime, I could have just as easily called it G or something.
Wait, it's not.
It just means I want to label this so it's close to this, but different.
It's not PAR, it's PRA, right?
Thank you. PRA. Good catch. Okay, so R is between P and A, and R prime is between A and Q. Right? I don't know if I want to spell out explicitly how we're using the postulates over there. But essentially, so here's what we have. We have a point. We know we have P, R, A, R prime, and Q. All these points have to be on the same line. Notice that P, R, and A, since R is between P and A, then P, R, and A are all on the same line. And since R prime is between A and Q, then all those 3 points are on the same line. Here's how I want to say it. Since we know PAQ, since we know PAQ, comma, AR prime Q, comma, and PRA, comma, then by axiom 2-1, comma, P, A, R prime, Q, oops, P, A, R, Q, what would we do on these? P, down here, P, R, A, R prime, and Q are all on the same line. We'll call it K. How do I know it? Since A is between P and Q, then A is on the same line as P and Q. Right? Since R prime is between A and Q, then R prime is on the same line as A and Q, which is still the line through P and Q. So we have the line through P and Q. We're going to call that line K. Okay. All right. Since A is between P and Q, A lies on line K.
Right.
That's using postulate 2.
So there's 2 points A.
Now A is 1 point.
What's over there?
We're showing that A being over here is an impossible picture. So right now, here's what we're doing. Here's PQ. Forget that line segment. Here's PQ. Here's A. We have an R and we have an R prime. Now I know that since A is between P and Q, then A, P, and Q are all on the same line, K.
What? How?
It's an impossible picture. We're doing proof by contradiction. But from postulate 2-2,
Is there a way?
from postulate 2-1, if we have B between A and C, then A, B, and C are 3 distinct points on a line. The only way you can talk about one object being between 2 objects is if there's one line through all those objects, right? They're lined up. That's the only way that there can be between. So I know A is between P and Q.
Yes.
So A is on the line that goes through the points P and Q. Okay. I know R prime is between A and Q.
Okay.
So R prime is on the line that goes through A and Q. But the line that goes through A and Q is the same as the line that goes through P and Q. So R prime is also on that same line. Similarly, R is on the line that goes through P and A. The line that goes through P and A is the same line that goes through P and Q. So all 5 of these points, P, R, A, R prime, and Q, are all on the same line. We call it line K. This is impossible picture. We're saying an impossible picture. We're doing proof by contradiction. In other words, our line looks something like this.
That's 1 line. Supposedly.
And that's one line, supposedly, which is impossible.
So
Now, how do I know that this is not a line?
it was true. Is there a way to prove that it was
was true is true.
Look, why is this picture impossible? Because our A is over here.
Yes.
If our A were over here, our picture would be fine.
Easy.
So I'm showing it's impossible for the A to be over here.
Yes.
I'm showing that if you put the A over here, then this line isn't really a line.
Okay.
That's what we're doing. And how do I know that this thing right here isn't a line?
Because a line is not.
Don't say because it's crooked. We don't know anything about crooked. Don't say because it bends. How do I know that this can't be a line?
Because it has more than one point.
Has a vertex.
Has an angle, I guess.
Yeah. That's just how I drift. Maybe, okay, maybe it comes, woo! All right, there we go. Loop-de-loop.
Goes an angle.
No, it's just one line. It's not two rays.
Um,
How do I know it can't be a line?
because there can only,
There are only
someone,
there's only one point and a line can
that's for
intersect
you,
another point.
There's only one point
That line can
where
intersect
two lines can intersect.
which is-
I know L1 is a line,
and it's intersecting,
and I know this thing intersects it at R and R prime.
which is right. Okay.
Which would make it a plane. Right?
No, which would mean whatever this curve is, it's not a line.
Right.
Because it intersects this line at 2 points. And a line can only intersect a line at 1 point.
Oh, yeah.
A. Then K intersects L1 at R and R prime. Contradiction. 9. Therefore, A is in the interior. Make sense?
Yes.
Now, technically, we didn't handle a case here. We didn't handle the case where A actually lands right on the angle. So we didn't handle the case where here's P, here's Q, and A actually lands right there. So I didn't bother saying this one because this one becomes pretty easy. Why can't this be the case? Then A is a point on line L1 between P and Q. Then P and Q are on the opposite sides of L1. But by definition, P and Q are on the same side because they're both in the interior.
Oh, right.
Oh.
So I didn't put that one explicitly in the proof, but sorry. I just read it. So if it's right there,
But wait. How is it unnecessary?
if A lies on one of the given lines,
Except for APA.
lines, comma, call it L1. So if A lies on one of the lines, call it L1. And it doesn't matter if it's right here or if A's down here. A's somewhere on the line, call it L1. Call it L1, comma. Then PAQ gives me P and Q are on opposite sides of L1, which would be impossible. 11. Therefore, A isn't on the lines. Okay, now we finished. Because if A was on one of the lines, then P and Q have to be on opposite sides of the lines, because A is between P and Q. But we know P and Q are on the same sides of both lines. That's what it means for them to be in the interior.
Right. Because in that circumstance, P and Q wouldn't be where they are right now. P would have to be on the other side.
Right,
Q would have to be
it's
on
an
the other
impossible picture.
side. Because Q
Right.
is in the middle.
Let's say a point between P and Q is right there. Impossible picture. Because that would somehow force P and Q to be on opposite sides of the line. Which is impossible because by definition, because P and Q are in the interior. And so by definition being in the interior, they're on the same side of both lines. Okay. That might be the hardest group in this section. Notebook, so we did 3, 4. Uh, 3, 5. R1 and R2 are rays of O, and R is a different ray from O. Then R lies entirely in the interior. So maybe this would be a good place to pick it up next. But let's go over what it's saying. It's saying if you have some angle with rays R1 and R2, and you draw some other ray, doesn't matter where, as long as the new ray isn't on R1 and R2, so some ray like this, here's our ray R, then the new ray is going to lie entirely in the interior, or it's going to lie entirely in the exterior of the angle. So that will be the next thing we prove. So we got 2 more proofs that we'll do next time. It'll be good to recap the interior one more time to do section 3.6. You can still get started on the homework. We'll say that the homework for exercise group 3.6 isn't due next time since we didn't finish the last section. The next time we'll do
3.6.
yeah, exercise group 3.6. That's the last one.
3.1 through 3.5.
So 3.1 through 3.5 is what we'll be doing. We should be able to finish this up next time, as well as cover chapter 4. Chapter 4 is easy. Okay, so good place to come back to it next time. Do we have any questions that we want recorded? Jump straight to homework?
Yeah.
Okay, let's turn this off and switch to homework.